Good afternoon, everyone. My presentation topic is a Voroni-inspired, a Voroni-inspired microstructure model to simulate cohesive strength in cold spray deposition. I will start by a brief introduction to the cold spray process and its involved mechanisms. Then I will explain our proposed models and the steps that we have to take to create that, followed by the numerical simulation, and I will conclude with the results. Cold spray process, actually in cold spray process, particles with hypersonic speed would hit the substrate and that make them bond to the substrate through the plastic deformation rather than melting. So the material can keep its properties and it has also lower level of residual stress. So cold spray is widely used in different industries, mainly for the repair and protective coating. It can somehow repair the fractured part, damaged part, without changing the microstructure, which is really important in some fields like aerospace and defense. Also, it has grown to be as a additive manufacturing technique, which is unlike the other fusion methods. It has a higher build rate and also has the lower cost. So cohesion in the cold spray mainly driven by two different mechanisms. The first one is mechanical interlocking. That happens when high-speed particle would hit the substrate and would create some craters on top of the substrate. So the successive particles would deform and anchor to those features and create a strong cohesive property. The other mechanism is metallurgical bonding. It happens on the high pressure localized on the impact surface. The oxide layer would crack and fresh metal to metal weld would happen. So the main driver in that process is severe plastic deformation. Many different studies try to numerically simulate the cold spray process. Many of single particle impact simulations only focus on one of those mechanisms. A few of multiple particle impact simulations consider both, but in with the cost of very high computational costs. So in this study, instead of simulating the particles individually, we generate the realistic cross-section of the cold spray deposit with multiple splat layers in Abacus using Python script. So we consider both metallurgical bonding and mechanical interlocking, and we try to incorporate different parameters like particle size, surface roughness, and flattening ratio, also oxide layer and bonding ratio. After that, we run a tensile test simulation in the Abacus and try to directly connect the cohesive strength to the particle parameters and process properties. We use Voronoi tessellation for the generation of the polygons. Actually, Voronoi tessellation is widely used in mechanical engineering and additive manufacturing to model lattice structures and biomimetic and porous materials. So to model the deposition, we start by placing grid points on a plane. So the grid spacing would be determined by two different parameters: splat, splat time, okay, splat width and splat height. That we calculate through average particle diameter and flattening ratio. But to mimic the randomness of the actual deposition, we introduced two different methods of randomization. In the first one, we each point would go in a random direction, displace in a random direction, with the distance that we calculate through the difference between particle diameter, average particle diameter, and a random diameter that we randomly choose from the particle distribution. And the second method is we apply a horizontal random shift to all the seeds inside odd numbered rows. So with that, we somehow introduce new randomness to the deposition that we see in the experimental data. And we also avoid very short Voronoi edges. So as you can see, okay. As you can see, not all the Voronoi cells are usable because some of them are lack the neighboring seeds. So we just consider the ones that are completely complete, and then we cut them in straight lines to create the structure, the final structure in Abacus. At this point, all the splats are in contact with the neighboring splats. But in reality, there is a oxide layer between them. In order to apply that, we slightly shrink all the splats by considering the oxide layer thickness. So to apply mechanical interlocking, we replaced straight lines with some zigzag, random size zigzag bumps in order to make the neighboring splats lock to each other. And because to prevent any kinds of possible overlap, we actually mirrored every pattern in one splat to the neighboring one. For metallurgical bonding, we introduced small rectangular bridges that would connect neighboring splats to each other, somehow mimic the metallic welding inside the actual deposition. The sizing and the position of the bridges is calculated through the when we divide the area of the somehow bonded area to the whole area in the SEM cross-section image. So after completing the numerical model, we then run a tensile test in Abacus And as you can see, there is somehow a uniform distribution of stress throughout the process, with the exception of 30% strain, that it somehow we have some high plastic deformation in the bridge area, which is mainly because of the mechanical interlocking part. And if we look to the stress strain curve, we can see that the simulation data is closely following the experimental data, with also the exception of the ending, which there is a decline. It's an ongoing research, and we are working right now to somehow modify the interlocking shapes in order to make the structure to resist better throughout the tensile test. So to sum up, we built a cross-sectional simulation of cold spray deposit using Voronoi tessellation in Abacus to avoid costly particle impact models, incorporate realistic features, particle size distribution, flattening ratio, oxide layer thickness, roughness, and metallurgical bonding bridges. The tensile test simulation showed potential to estimate cohesion strength directly from feedstock properties and spray parameters. And it provides a faster, more flexible framework that captures both mechanical interlocking and metallurgical bonding, and can be extended to different materials and conditions. Thank you for your attention.